Welcome everyone. Today's speaker, our second speaker, is Michalina Borczynska, who will present her master thesis about singular symplectic reduction via orbifolds. Michalina, the floor is yours.
Thank you for introducing me and my presentation. So, as you said, my master thesis is about singular symplectic reduction via orbifolds, and that is also the topic of this presentation. So, symplectic reduction is a procedure when we have a symplectic manifold possessing some symmetries associated with the group action, and we reduce this symplectic manifold to a lower dimensional one that also carries an induced symplectic form. And the Marsden, Meyer, and Weinstein established the theorem that describes the regular symplectic reduction procedure. And in this regular case, the reduced space has a structure of a smooth manifold. However, when this reduced space is not a smooth manifold, the reduction is called singular, and we have spaces that are no longer smooth manifolds, and we need some more general structures to describe them. And then the theory that becomes particularly useful is the theory of spaces called orbifolds. And my master thesis studies singular symplectic reduction through the framework of the so-called symplectic orbifolds, which are orbifolds with defined on them symplectic structure. And also this thesis investigates its physical applications. So, in order to talk about, I don't know how to remove it. In order to talk about symplectic reduction, we have to introduce the notion of momentum maps, and that one requires the notion of fundamental vector field. So suppose that we have a Lie group action on a smooth manifold, and then the fundamental vector field corresponding to some Lie algebra element will be the vector field on our manifold M, given by the following condition for each point on this manifold. And then suppose that we have a symplectic manifold and also Lie group action on this manifold, that is it's symplectic, that means it preserves this symplectic form. And if for each Lie algebra element the corresponding fundamental vector field is Hamiltonian, then we can define a linear map, lambda, defined as follows, and called comomentum map for this Lie group action, and also the corresponding map called momentum map, which is the map from our manifolds to the dual of the Lie algebra. So now I will sketch what is the idea of the Marsden, Meyer, and Weinstein regular symplectic reduction. So suppose that we have a Hamiltonian system that is the smooth manifold, the symplectic form on it, and also some Hamiltonian function, and that it has symmetries induced by some Lie group action. That is, this Lie group action preserves the symplectic form and also the Hamiltonian function. And also suppose that this Lie group action admits a momentum map. And when we choose an element from dual to Lie algebra, such that the level set of this momentum map will be a submanifold of our manifold M. And then we also consider a Lie subgroup of G mu of this Lie group G that preserves our level set of the momentum map, and also the orbit space given by the quotient of this level set by this Lie subgroup. And when this G-mu action on this level set is free and proper, then this quotient will be a smooth manifold, also equipped with a symplectic form, which is compatible with our initial symplectic form, and also equipped with Hamiltonian function that is compatible with our initial Hamiltonian function. And now we can consider the Hamiltonian, such Hamiltonian vector field XH on our initial manifolds, and also such Hamiltonian vector field XH mu on the reduced manifold. And then it turns out that the integral curves of XH mu can be used to obtain in a simple manner the integral curves of vector field XH, whose image will be contained within this level set of the momentum map. And that is what we are interested in when we are dealing with some mechanical systems and their evolution. However, when this level set is not a submanifold, or such a quotient fails to be a smooth manifold, then this construction of a compatible symplectic structure on this quotient is singular, and then what becomes useful is the theory of orbifolds. So now I will introduce the orbifold structure. And to do this, I first will say what is the single orbifold chart. So suppose that we have a topological space, and then an n-dimensional orbifold chart for some open subset for this topological space will be a triple, consisting of a connected open subset of n-dimensional Euclidean space, also a finite group which acts smoothly and effectively on this utility open subset, and also a continuous map from this utility subset to our topological space, which is invariant under this group action, and also induce the following homomorphism between this open subset of the topological space and such a quotient. Okay, but this was a single orbifold chart, but we need more charts, and also we want to know what does it mean for those charts to be compatible with each other. So for that we introduce the definition of embedding between orbifold charts. So suppose that we have two n-dimensional orbifold charts for some topological space, and if the first utility one open subset embeds in the second utility open subset by the smooth embedding lambda, and also the diagram on this picture is commutative, then this lambda is also called an embedding between whole orbifold charts. And that enables us to define the whole orbifold atlas for some topological space, and it will be the collection of n-dimensional orbifold charts, which will cover the whole topological space. And also, if we have two charts from this collection that intersects on this topological space, then we can always find a third chart in this collection that embeds in those previous two orbifold charts. We also need to say that an orbifold atlas 8 will refine an orbifold atlas B if every chart in 8 will admit some embedding into some chart of B. And then we say that two orbifold atlases will be equivalent if there exists an orbifold atlas that will refine both of them. And now we can say what is the whole orbifold. So it is an n-dimensional. So an n-dimensional orbifold will be a paracompact Hausdorff topological space, also equipped with an orbifold structure that is an equivalence class of n-dimensional orbifold atlases for this topological space. And now I want to equip the orbifold with a symplectic structure. So first I will say what is the differential form of an orbifold. So we consider on the orbifold a maximal atlas and associate with each chart from this maximal atlas a local differential K-form. And we also want those differential K-forms to be invariant under appropriate group action and also to be compatible with each other, where the compatibility condition is given by the pullback of the appropriate embedding. And then a symplectic form on an orbifold will be a two-form on the orbifold, where the associated two forms are just symplectic forms on each of the open subset U tilde, and a symplectic orbifold will be a pair of the orbifold together with a symplectic form on it. Okay, so now I will give an example of singular symplectic reduction when the reduced space is a symplectic orbifold. So we can consider the n+1 copies of the complex plane together with the canonical symplectic form on it, and also the Lie group action of a circle group given by rotation by appropriate angle of each of the complex number. And then one can check that this action is actually symplectic and also admits a momentum map, which is in that case just a smooth function on our manifold. And also we can show that for any negative number, the orbit space given by the quotient of our momentum map level set by the circle group can be equipped with the orbifold structure and also become a symplectic orbifold with a symplectic form induced by this initial symplectic form omega. And this orbit space is also called the weighted complex projective space. So to sum up, orbifolds generalize the notion of a manifold and allows for the presence of some singularities that are associated with finite group actions. And they are particularly useful when we study singular symplectic reduction, where one deals with quotients spaces by Lie group actions. And currently in my master thesis, we are investigating physical applications and example of singular symplectic reduction with this orbifold setting. And for instance, we study the reduced phase space of rigid body mechanical system and also a reduced physical system from lattice gauge theory. So that is all. Thank you for the attention.
Thank you very much for a very interesting talk. Are there any questions? Well, if not, I have some. Could you present, or I mean, could you give a very, or just an example of orbifolds in classical mechanics? For instance, I mean, how exactly do they appear in a rigid body?
Yeah, I mean, yeah. So the example I am studying now, it's the spherical pendulum, but there are some problems. So I do not want to tell you something which is not true. But I think it can be orbifolds like partially, you know, that it appears there, but it's not the whole orbifold. So yeah, I don't know like the example where the whole reduced space is a orbifold from the mechanical systems. Yeah, so maybe it's a part of it is an orbifold. Yeah, but yeah, something like that.
Okay, I see. And can you give any other example in classical mechanics of orbifold?
Not really now. I don't
Okay.
think so.
Okay, yeah, sure. Um, okay, just one more question about the rank of a symplectic form on an orbifold. I mean, could you comment on that? Does it change or how it behaves on an orbifold? The characteristic distribution of a symplectic form.
On an orbifold?
Yes,
Mm,
yes.
mhm. I don't think I can tell you much about this, but I will check it out then, because I'm not sure now.
Okay, no problem. So are there any questions and remarks? Okay, if not, thank you very much once again, as I said, for a very interesting talk. Thank
Thanks.
you.